Welcome. A little bit more about quivers, a beautiful class of geometric objects. They generalize both multigraphs and finite simple graphs. I also like to think about a class of graphs which have no multiple connections. So you're allowed to have a finite simple graph, you're allowed to have loops, but no multiple connections. I call this non-magnetic because of these Schrödinger pictures, where you have associated to functions on the edges, magnetic part, and functions on the vertices as a scalar function part. And we have seen that in very generality for all quivers we have this upper bound on the eigenvalues of the Kirchhoff Laplacian. I overstepped a little bit with the lower bound, which is this weak Brouwer-Hemmers bound, which is actually only true for non-magnetic, in the non-magnetic case. So you cannot have multiple connections. In the proof, I was actually assuming that, and I said, okay, you know, in general, what happens if you add edges, what happens is you increase the energy. But then you also increase the degree, so it doesn't actually kind of work. And I will talk about this, what happens when you increase if you increase the number of connections, kind of if you add more connections, or what happens if you add more loops. So there, this is, in both cases you get more energy. That's what I wanted to talk about here. But in this case, there's a simple example where it is wrong is this example. So we have two vertices and two loops here, and in this case this bound already does not work. So that was one of the amendments I wanted to make. These are two theorems. This class and this class, both classes are invariant under, if you take the principal submatrix of the Kirchhoff matrix, then you get again a Kirchhoff matrix of in the same class. So that made the induction easy. That's not true for finite simple graphs, and it's also not true for multigraphs, because we add loops when we do that. And then we remove one of the rows and columns. What happens if we add more loops somewhere else? I also talked about the Schrödinger case. This is one of the reasons why I like quivers. I like quivers because what happens is you can associate to the loops which you have here. You can model with this a scalar potential which you attach to the vertices. And these are integer, these are by a priori integer values here. But then, of course, you can just divide the whole matrix by some constant. And this estimate here, not this, but this estimate here is fine with respect to this scaling. Right? If you divide the matrix by 10, the eigenvalues get divided by 10, and also the diagonal entries get divided by 10. What is not true is I kind of also stated that you can shift the energy. When you shift the energies, of course this shifts, but there's also this gets shifted by 2 times that. What you have to assume here both, that this V for the bound here, for this bound here, this general bound for magnetic Schrödinger operators on a general quiver, this is true, but only if V and W are bigger or equal to 0. And this V and W essentially just can be incorporated into the geometry. So I like that, to have the potential, to have the field geometric part, the field part also as geometry. So that's really cool. So that's what I wanted to say about it today. Just some kind of, you know, low-hanging fruits, but I like it because it's relatively simple and beautiful. So, and also intuitive. So what happens, for example, if you add another loop? I, by the way, have an example here of a quiver, and so everything is computed here. So we have 3 vertices, we have 11 edges, and so the loops are counted as edges, And then you have here the diagonal entries of the Kirchhoff matrices D1, D2, D3. This is the vertex cardinalities, right? If you look here, so this has 4 plus 2. This has a vertex cardinality 6, vertex degree 6. This is 5, and this is also 5. So we can also look at the loops. I look at the loops, the number of loops you have at the vertex k, and then you can estimate this. This generalizes the fact that the eigenvalues are non-negative for a quiver, but you can say more. Right? And I showed last time that this the argument y lambda k is bigger or equal to 0, and it follows essentially from k is equal to ftf. This is a kind of positive semi-definite if you have this decomposition, which is the divergence of the gradient. And the gradient is that, in this case, this matrix which maps your functions on vertices to functions on edges. So this is a map which maps you a three-dimensional vector into 11-dimensional vector. String theorists might like that. But and then we have also the K1, which is the when you switch and you take f. So this is actually just FFT. This is a function on, or a matrix on functions on edges, which is the one form. So this is typically, I mean, what you have also in classical mathematics. This is when you have that. This is where electromagnetism happens, right? So you have a one forms, and so one form is, for example, the electromagnetic potential is a one form. And you take the derivative, exterior derivative, you get the electromagnetic field, and that's what you can do also in graph theory. So this is essentially isospectral in the sense that they are just up to eigenvalue 0. They are the same. The pseudo-determinant are the same. So this is an example. And what I wanted to say, just two things. First of all, yeah. So this, in general, what happens if you increase the degree, where you'd add loops, right? But if you add a loop at the point, what you just do is you increase the energy, and so that was what happens here. And actually, this is just linear algebra. There is a nice book of Horn and Johnson on matrix algebra which covers this part. It's going back to a result of Hermann Weyl from 1912. And so what happens if you take a matrix and you add a positive semi-definite matrix to it, and then you can say something about the eigenvalues. So here we can use this, of course, with the case when B is the Kirchhoff matrix of the underlying graph without loops, and here we just add the loop diagonal matrix, and then this is directly that consequence of that matrix inequality, of this eigenvalue inequality of Weyl. So that's pretty cool and pretty intuitive, right? Increasing the function here, if increasing the potential on the vertices, that only increases the eigenvalues. For a multigraph, you have always an eigenvalue 0. And actually, this is something maybe I could state somewhere else. This is kind of a little corollary. K is invertible, if and only if there is no multigraph connected component. So if you have a multigraph connected component, of course, this connected component has an eigenvalue 0, so it's not invertible. So that's kind of just a consequence. So if you add a loop, what actually happens is you automatically also add. And if you add a loop, you also increase the eigenvalues. But this you can understand also using the Hadamard variation formula, which is then kind of the key for understanding this. So what happens if you add, for example, also here, if you take that molecule, right? So this has less energy than when you add another bond. So it contains more energy, more binding energy in some sense. What happens if you add one edge more? What happens? But this is you can also understand just by deformation. I think this Hadamard, this Hadamard deformation formula, probably everybody has just, it's so simple to discover. So you don't have to read any book on perturbation theory or anything. You kind of just do it. So when you have a ku is lambda u and you differentiate that, you get k prime u plus k u prime is lambda prime u plus lambda u prime by the Leibniz formula, and then you take so you can write this as k prime minus lambda prime u is equal to lambda minus k u, and then you dot that thing with a u again. So you dot that with a u. So we have the k prime minus lambda prime u dotted with u is equal to, and then when you dot that with u here, so when you take lambda minus k u dotted with u, so we have just dotted it with u here, and you can take the lambda minus k on the other side. Oh, this is u prime. This is u prime. So when you take the lambda minus k, because it's symmetric, you take it on the other side, you get lambda minus k u, which is equal to 0. So that's equal to 0. And then you get that tells you that lambda prime, so from this you get lambda prime is equal to k prime u u, the dot product of k prime u u. Using that we have a u has length 1. So that's the statement which you have here. So what happens if we are changing, say, if you turn on another edge here, and we smoothly do that by just taking, changing here plus t here, plus t, and here minus t. That's what happens when you are doing, when you turn on, this is what happens when you, and t is equal to 1, you have just added one more edge. And so then the vertex degree here and here has both changed by 1, but you have also a minus 1 here because of the adjacency matrix part. So it's a deformation thing. But then if you look at that, in this case, what is actually this formula tells us, this is then just if you take an eigenvector which has length 1, so you get the k a so the derivative, if you take the derivative, you get the 1 here, minus 1 here, minus 1 here. So what you get, the ua times ua, so ua square, these are components, plus ub square, these are these two parts, minus 2 ua ub. And that's just ua minus ub squared, which is bigger or equal to 0. So when you deform that, the eigenvalues, what happens is the eigenvalues only can increase. So that's the argument. And you can see also if you are in a situation where you have a multigraph and no loops, what happens is if you have a multigraph, no loops, then you have always an eigenvalue 0, the constant eigenvector, and then that is 0. So if you add another loop for the grounds, for the 0th eigenvalue, this doesn't change, and it remains a 0 eigenvalue. So it's kind of, but if you have an eigenvector which is not constant, or if ua is not equal to ub, then you get already a slope. But what happens is that's the reason for this inequality. So both changing the scalar part of the Schrödinger operator or changing the magnetic part can only increase the spectrum, the eigenvalues. And that's something which is very natural if you think about kind of these as energy spectra of, I mean, these are eigenvalues, these are related to frequencies with which that molecule swings, for example, when you are exciting it. And so, or quantum mechanically, what are the energies of the quantum mechanical system? And so if you add an edge or you add more energy to a loop, what happens is you can only increase the energy. Okay, that's what I wanted to say today.